A robotic hand in Beijing just lifted 50 kilograms while weighing 370 grams. That is 135 times its own body weight, lifted by a hand small enough to fit inside a winter glove. For comparison, if a 200-pound man lifted that same ratio, he would be curling a small car over his head with one arm. Engineers who study robotic grippers for a living called the number almost unbelievable when it first showed up in a product spec sheet. And the company behind it is not a secretive military lab. It is a 2-year-old startup that is now being valued at $6 billion, built by a founder who says the whole idea started with a cartoon he watched as a kid. Today we are breaking down exactly how a machine this small got this strong, why the rest of the robotics industry has been stuck on this exact problem for years, and what it means now that China appears to have quietly solved it. For decades, the rule in robotics was simple and unforgiving. If you wanted a robot that could lift something heavy, you built it heavy. Industrial robot arms on car factory floors can lift over 1,000 kilograms, but they weigh as much as a small truck to do it. Their strength comes from thick steel frames, oversized motors, and gearboxes the size of a beer keg. That trade-off worked fine when robots lived inside a fenced-off cage on a factory floor, bolted to the concrete, never expected to move or to work anywhere near a human being. Nobody cared how much the arm weighed as long as it never had to leave its station. For years, the entire industry built around one assumption: strength and weight move together. If you wanted 10 times the lifting power, you accepted 10 times the bulk, the cost, and the danger. Researchers did try to sidestep this problem years before humanoid robots became a mainstream headline. Back in the 2010s, labs at places like Harvard and MIT experimented with soft robotic grippers, origami-inspired designs made from fabric and rubber that could gently wrap around an object and lift up to around 100 times their own weight. It was a clever trick, and it proved the ratio itself was not impossible. But those soft grippers traded away almost all precision to get there. They were brilliant at gently scooping up a single round object, like a ball or a piece of fruit, and nearly useless at anything that required actual fingers, like turning a screw, pressing a button, or picking a single sheet of paper out of a stack. Chinese labs ran their own versions of this experiment too. Researchers at the University of Science and Technology of China built magnetic soft grippers gentle enough to lift a dandelion puff without damaging a single seed, and separately built pneumatic muscle-driven grippers that could hoist over 35 kilograms using a winding, snake-like grip inspired by how an elephant wraps its trunk around a branch. Every one of these was proof that huge lifting ratios were achievable. None of them were proof that you could combine that strength with the fine control of an actual hand. Then, humanoid robots showed up, and that old rule turned into a wall. A humanoid robot does not get to bolt its hand to the floor. It has to carry that hand at the end of an arm, which is carried by a torso, which is carried by 2 legs trying to balance on uneven ground. Every extra gram in the hand becomes a problem for the shoulder motor holding the arm up and for the leg motors keeping the whole thing from tipping over. Engineers ran into a brutal catch: make the hand strong enough to be useful in a warehouse or a factory, and it gets too heavy and too slow to move like a human hand. Make it light and fast, and it can barely grip a coffee cup, let alone a toolbox. Give it the gentle wrap of a soft gripper, and it can lift almost anything round, but hand it a screwdriver, and it is completely lost. For years, this was treated as close to a law of physics. You could have power, or you could have grace, or you could have precision. Picking 2 out of 3 was considered a good result. Getting all 3 into a single hand small enough to belong on a human-sized robot was the part nobody had actually pulled off. Before we get into how one company appears to have broken that trade-off, hit that subscribe button so you do not miss the next deep dive into what China is quietly building in robotics, and drop a comment telling me which humanoid robot company you think is actually going to win this race, because the answer might surprise you by the end of this video. The company that pulled this off is called Linkerbot, founded in Beijing in 2023 by a robotics engineer named Alex Zhou. Zhou has told reporters the spark for the whole company came from Doraemon, the Japanese cartoon about a robotic cat with a magic pocket that produces any gadget its owner needs. As a kid, Zhou assumed the pocket was the trick. As an adult with a robotics degree, he realized he had it backwards. The pocket does not matter if you do not have hands capable of using what comes out of it. A robot with an infinite toolbox and clumsy fingers is still useless. The real magic, he decided, was never the gadgets. It was always the hand. That single realization became the entire foundation of the company. So how do you build a hand that weighs about as much as a smartphone but can hold up a small motorcycle? The answer is not one single breakthrough. It is a stack of smaller engineering decisions that each shave weight or add strength layered on top of each other until the ratio flips in your favor. Start with the materials. Most industrial grippers are built from metal because metal is strong and predictable under load. But metal is also heavy, and every gram in a finger has to be dragged around by everything upstream of it. Linkerbot's engineers switched large sections of the hand to a specialized engineering polymer called PEEK, a plastic that aerospace and medical device makers already trust because it holds its shape under heavy repeated stress without cracking, and it does this while weighing a fraction of what steel weighs. Think of it like the difference between a bridge built entirely from solid iron beams and a modern bridge built from high-strength composite cable. The composite version can hold just as much weight, sometimes more, while using a small percentage of the material. That is the same logic packed into a hand small enough to close around a pen. Next comes the transmission, which is the mechanical link between the motor and the finger that actually moves. This is where most lightweight robotic hands quietly fail. A tiny light motor simply does not produce enough raw force on its own to lift 50 kilograms. So Linkerbot leaned on something engineers have used for over a century to solve exactly this problem: gear reduction. Picture a bicycle. In its lowest gear, you can pedal a heavy cargo bike up a steep hill using barely any leg strength because the gearing trades your speed for your force. You spin the pedals many times to turn the wheel once, but each turn of the wheel carries far more force than your legs alone could apply directly. Linkerbot's O6 hand uses a worm gear transmission built around in-house designed micro-reducers, engineered specifically to be small enough to fit inside a finger joint while still multiplying the motor's output by a huge factor. The company builds these reducers itself rather than buying generic parts off the shelf, which is part of why the finished hand can be tuned so precisely for this exact strength to weight target. Here is the number that actually deserves its own moment. The finished O6 hand weighs 370 grams, roughly the weight of a full can of soda. It is rated to handle a 50-kilogram load, more than the weight of most adult humans. That works out to being 135 times its own weight, a ratio the company's own engineers have described in interviews as a genuine engineering milestone, not just a marketing number. And this is not a one-off lab demo built to impress a camera crew once and then quietly retired. Reuters reported that Linkerbot is already manufacturing close to 5,000 of these hands every single month, with plans to scale that up to 10,000 units monthly in the near future. This thing is not a prototype sitting in a glass case. It is shipping. The hand also is not a one-trick strongman. The same design that lets it lift 50 kilograms also lets it perform tasks that require the opposite of raw strength. Company demonstrations show the hand threading a needle, a task that demands positioning accuracy down to roughly 0.2 of a millimeter, tighter than the width of a human hair times 2. It can grip something as delicate as a soft, deformable object without crushing it, and in other demonstrations it has been shown rapidly turning screws with the kind of speed and precision you would expect from an assembly line worker who has done the same motion 10,000 times. That is the part that makes this genuinely different from a simple hydraulic claw. A hydraulic claw can crush a bowling ball. It cannot pick up an egg without breaking it. Linkerbot's hand is being asked to do both in the same fingers, switching between them in seconds. The O6 is actually the entry-level model in a much wider lineup, and this is where the strategy becomes clearer. The full Linker hand family spans anywhere from 6 degrees of freedom on the O6 up to 42 degrees of freedom on the most advanced research-grade versions. Degrees of freedom being the engineering term for how many independent ways a joint can move, which is essentially the measure of how close a robotic hand gets to matching the flexibility of a human one. At the industrial end sits the L20, built around what the company calls a super electric cylinder, a compact linear actuator rated for around 200 newtons of thrust at 90% drive efficiency, tested to survive more than 1 million movement cycles before wearing out. At the research end sits the L30, tuned less for brute strength and more for the kind of repeatable, needle-threading precision that university robotics labs and high-end manufacturers are willing to pay a premium for. Instead of building one hand and hoping it fits every customer, Linkerbot effectively built an entire menu, letting a warehouse buy raw lifting power while a university lab buys fine motor control, all sharing the same underlying manufacturing platform. That platform is also where the real strategic weight of this story sits. Behind every one of these hands is something called Linker which the company describes as the largest real-world dataset of dexterous manipulation skills currently in operation, built from more than 500 distinct captured behaviors, everything from twisting a bottle cap to folding fabric. Every hand shipped out into a factory or a lab is quietly feeding data back into that system, and every improvement to the underlying skill set can, in theory, be pushed back out to every hand already in the field through software rather than a hardware redesign. And in a detail that sounds almost like science fiction until you realize it is already running in production, some of Linkerbot's factories in Beijing and Shenzhen are now using dexterous hands to manufacture other dexterous hands, robotic hands performing the delicate assembly work needed to build the next batch of robotic hands. That is not a research paper claim about what might be possible someday. According to the company, it is a working production line today. Now here is the part that a lot of the breathless headlines around this story tend to skip entirely. 50 kilograms is the rated maximum load under specific controlled conditions, not the number the hand is casually lifting all day in a warehouse. Engineers who work with robotic grippers point out that a headline strength figure like this usually describes a best-case scenario, often a straight, symmetrical grip on a rigid object positioned exactly where the fingers can apply maximum leverage. Ask that same hand to grip an oddly shaped, off-balance load at an awkward angle, the kind of thing a human warehouse worker deals with constantly without thinking twice, and the safe working load drops well below that headline number. This is true of essentially every strength claim in robotics, from industrial arms to humanoid grippers, and it is not unique to Linkerbot. It is simply the gap between a spec sheet and the messy real world that spec sheets are tested in. There is a second honest catch worth naming here. A hand this light achieves its strength partly by using specialized polymers and micro-engineered gear systems instead of thick, forgiving steel. Lighter, more precisely tuned components generally have a narrower safety margin before something wears out or fails, which is exactly why Linkerbot emphasizes that its polymers are self-lubricating and corrosion-resistant. Engineering choices clearly aimed at extending the working life of a mechanism that has less structural material to fall back on if something goes wrong. Whether these hands hold up to years of continuous factory use, the way a bulky old-fashioned steel gripper does, is something that will only really be proven over time, not in a 2-minute demo. Video. It is also worth saying plainly that most of the performance numbers circulating about this hand come from the company itself, and from interviews its executives have given to journalists. So, as always, healthy skepticism toward company-reported figures makes sense until independent third-party testing catches up. And Linkerbot is not competing in an empty field, which is worth remembering before crowning any single company the winner. Other Chinese firms are chasing the exact same strength-to-weight target from different angles. Wuji Hand, built by a rival startup, uses 20 separate joints packed into a 600-gram hand and claims it can lift around 20 kilograms while still performing delicate cutting tasks. Agibot, another major player in China's humanoid robotics scene, recently unveiled its own dexterous hand built around vision-based tactile sensors rather than raw lifting numbers, betting that sensing and touch feedback will matter more than headline strength once these hands are actually working around people. None of these companies has fully cracked every part of the puzzle at once, but together, they show this is not one lucky engineering team stumbling onto a fluke. It is an entire national industry converging on the same hard problem from multiple directions at the same time, which historically tends to produce faster progress than any single company working alone. Zoom out, and this is not really a story about one clever hand. It is a story about who controls the component that every humanoid robot on Earth is going to need. Tesla's Optimus, Figure's humanoid robots, and dozens of other American and European projects all need dexterous hands, and right now, most of them either build their own in relatively small numbers or shop for suppliers in a market where Linkerbot claims to already control more than 80% of global market share for high degree of freedom robotic hands. That is not a small statistic. If accurate, it means that when the next wave of humanoid robots rolls off assembly lines anywhere in the world, there is a real chance the part doing the actual gripping, the single most mechanically complex part of the entire robot, was designed and built in Beijing. This fits a pattern that shows up again and again across China's advanced manufacturing push. Rather than trying to build the flashiest, most headline-grabbing finished product first, Chinese firms have repeatedly focused on cornering the unglamorous middle layer of a supply chain: the batteries, the rare earth processing, the specialized motors, the components everyone else needs but few companies actually want to spend years perfecting. Linkerbot's own backers include state-linked investment funds alongside private capital from firms like Alibaba's Ant Group, which suggests this is not viewed inside China as just another startup chasing a trend. It is being treated as strategic infrastructure for an entire coming industry. Competing Chinese firms like Unitree, which recently filed for its own stock market listing seeking a valuation up to $7 billion, show this is not a single company's bet either. It is a full ecosystem racing forward at the same time, each company solving a different piece of the humanoid robot puzzle. Investor interest in the whole sector reportedly surged after Unitree's robots put on a widely watched televised demonstration, and after humanoid robots took part in a public half-marathon in Beijing. The kind of stunt that looks like a gimmick right up until it becomes the moment a whole industry gets taken seriously by investors who were previously on the sidelines. Not every Chinese robotics company is even chasing the same goal. While Linkerbot leans hard into high-value precision work, skills like massage therapy or assembly line craftsmanship that command a premium over basic manual labor, other domestic competitors such as X-Square Robot are explicitly training their hands for a completely different market: ordinary household chores, laundry, dishes, tidying a kitchen counter. That split matters, because it means China is not betting its entire robotics industry on one use case. It is simultaneously building toward the high-end industrial buyer and the ordinary consumer household, often with hands descended from the same underlying research into strength-to-weight ratios that started this whole story. The open question nobody can fully answer yet is what happens when hands like this one get bolted onto millions of humanoid robots working in homes, hospitals, and warehouses around the world. Does a genuinely dexterous, strong, lightweight robotic hand mean cheaper elder care and safer warehouse jobs, taking on the repetitive lifting that wrecks human backs and shoulders over a career? Or does a component this capable, this cheap, and this dominant in global supply simply accelerate how fast physical labor gets automated, faster than most economies are prepared to handle? Joe himself has said publicly that he sees these hands eventually performing tasks like massage therapy or even assisting in dentistry, skills he describes as worth several times more than basic manual labor. That is either an exciting glimpse of what dexterous robotics can unlock for human well-being, or it is a preview of just how far up the skill ladder automation is now willing to climb. Maybe it genuinely depends on which industries adopt this technology first and how carefully the transition gets handled. Either way, the numbers on that spec sheet are real. They are shipping in the thousands every month, and the gap between what a robotic hand used to be able to do and what one now weighs while doing it has quietly closed faster than almost anyone in the industry predicted. What happens next probably depends less on the engineering, which increasingly looks solved, and more on how quickly the rest of the world decides to catch up, or decides it needs to at all.